Hi everyone, I am Radhakrishna. Welcome to this video lecture on Unit 2 Mechanics of Particles. In this video lecture, I would like to explain the topics elastic oblique collision, impact parameter, and scattering cross section. The first topic is elastic oblique collision. If before collision and after collision the particles confined to a single plane and are moving in different directions, then the collision is said to be oblique collision. This can be explained as, consider a particle of mass m1 moving with a velocity u1, making an angle alpha along the collision axis. This is the collision axis. The second particle of mass m2 is moving with velocity u2, making an angle beta with the collision axis. After collision, the first particle is moving with velocity v1, making an angle theta with collision axis, and the second particle of mass m2 moving with velocity v2, making an angle phi with collision axis. Now, this can be written as, let two bodies of masses m1 and m2 be moving in different directions with velocities u1 and u2 respectively, making angles alpha and beta collide with each other. After collision, the two bodies move in different directions with velocities v1 and v2 respectively. This is called two-dimensional oblique collision. After collision, the two particles moving with v1 and velocities v1 and v2, making angles theta and phi along x-axis, along collision axis. The line joining the centers of the two bodies at the time of collision and the line perpendicular to each in the plane of paper are taken as reference axis. Since the velocities of the bodies along y-axis is unaffected, the components of the particles along y-axis are same. Hence, v1 sin theta 1 is equal to u1 sin alpha, v2 sin phi is equal to u2 sin beta. In the diagram, the velocities of components along x-axis are not shown. They are, before collision, the component of u1 along x-axis is u1 cos alpha, along y-axis u1 sin alpha, and the component of u2 along x-axis is u1 u2 cos beta, and along y-axis u2 sin beta. After collision, the component of v1 along x-axis is v1 cos theta, along y-axis, along negative y-axis v1 sin theta. The component of v2 of the second particle along x-axis v2 cos phi, and along negative y-axis the component of v2 is v2 sin phi. Now, by Newton's law, V2 cos phi minus V1 cos theta is equal to U1 cos alpha minus U2 cos beta. This can be derived as before and after collision the relative velocities are same. Now, according to law of conservation of linear momentum, we get m2 v2 cos phi plus m1 v1 cos theta is equal to m2 u2 cos beta plus m1 u1 cos alpha. That is equation 4. Here we have 4 equations and we have determined 4 unknown quantities v1, v2, theta and phi. Now, multiplying equation 3 by m2 and then subtracting equation 4 from it, we get v1 cos theta is equal to m2 minus m1 by m1 plus m2 into u1 cos alpha plus 2m2 by m1 plus m2 into u2 cos beta. Here the complete derivation is not necessary. Similarly, multiplying equation 3 by m1 and then adding it to equation 4, we get v2 cos phi is equal to m2 minus m1 by m1 plus m2 into u2 cos beta plus 2m1 by m1 plus m2 into u1 cos alpha. From equations 5 and 6, we can solve v1 and v2 as squaring and adding equations 1 and 5, we get v1, and similarly squaring and adding equations 2 and 6, we get v2. The angles theta and phi can be found by dividing equation 1 and equation 5 and equation 2 and equation 6 respectively. Now, special cases. If u2 is equal to 0, that is the second particle is initially at rest, then from equation 2 v2 sin phi is equal to 0. In this equation, as v2 is not equal to 0, that is after collision the second particle is moving with velocity v2, hence sin phi is equal to 0 or phi is equal to 0. That means if the sphere or particle of mass m2 were initially at rest, it will move along the line of impact after collision. Second case, if u2 is equal to 0 and m1 is equal to m2, then from equation 2 phi is equal to 0 and from equation 5 theta is equal to 90 degrees. This shows that if a sphere or particle of mass m impinges obliquely on another sphere of same mass at rest, the direction of motions of the spheres after impact will be at right angles to each other. Third case, if two equivalent perfectly elastic spheres collide at right angles, their directions after impact will still be at right angles. In this way, we can describe the two-dimensional oblique collision. If the collision between two particles are in space, that is not confined to a single plane, then the collision is said to be three-dimensional collision. The example of three-dimensional collision is when two airplanes traveling in air, if they collide each other, then the collision is three-dimensional collision. Now, I would like to explain two important short points: impact parameter and scattering cross section. First point is impact parameter. Consider a positive particle like an alpha particle approaching a massive nucleus n of the atom. In the diagram, this is nucleus n, it has positive charge. and an alpha particle is at A, is moving towards nucleus along this direction. Alpha particle has also a positive charge. Hence, due to Coulombic force of repulsion between nucleus and alpha particle, the alpha particle follows a hyperbolic path AB with nucleus N as its focus. In the absence of repulsive force, the particle would have followed the straightened path AC. That means, due to repulsive force between nucleus and alpha particle, the alpha particle is moving along this path. This path is hyperbolic path. If there is no repulsive force between nucleus and alpha particle, the alpha particle is moving along this direction, that is along direction AC. Now, the perpendicular distance between initial direction AC of the alpha particle and nucleus is Nm. This perpendicular distance is P and is called as impact parameter. This can be defined as impact parameter is defined as the closest distance between nucleus and positively charged particle projected towards it. This is also known as collision parameter. Now, the second topic is scattering cross section. Scattering cross section. When a beam of alpha particles are projected into a thin metal foil, they are scattered in different directions. In the diagram, alpha particle beam is traveling along this direction. This is scatterer, that is a metal foil. After scattering, the alpha particles are deflected in this cone of direction. The third angle of the cone is d omega. This can be explained as, let n be the incident density, that is the number of incident particles crossing per unit time a unit surface placed perpendicular to the direction of propagation. In this n particles, suppose dn be the number of particles scattered per unit time into solid angle d omega located in the direction theta and phi with respect to the bombarding direction. Then the ratio dn by n is called scattering cross section. Thus, the scattering cross section in a given direction is defined as the ratio of the number of scattering particles into solid angle d omega per unit time to the incident density, that is scattering cross section sigma Sc is equal to dn by n. So, you have to study and read carefully the topics oblique collision, impact parameter and cross section. Thank you. All the best.